This is the first in a series of resources that look at matrix algebra. We define and provide basic information about matrices. We consider the operations that allow us to manipulate matrices. We discover how to use the row operations to solve a system of equations using matrices. We consider various operations on pairs of matrices, including adding, subtracting, linear combinations, and multiplying. We learn how to find the inverse for a matrix. We discover the determinant for matrices and learn how determinants allow us to solve systems using Cramer's rule. A matrix is a rectangular array of numbers. A matrix, which we name using a single capital letter, is basically a box into which we throw appropriate numbers. These numbers are arranged into horizontal rows and vertical columns. When we read off a matrix, we read from left to right across the rows and work from the top down. Why would we want to create these matrices? They provide a method for working on systems of equations without dealing with the actual variables. This is very useful when we want to program a computer to deal with calculations and solving. We create a matrix by placing the coefficients for the variables into the same column. We will have a column for the x coefficients, the y coefficients, etc. When we set up a matrix, we cannot have any empty positions. If a variable is missing from an equation, we have to place a 0 in that position. We can also create what is called the augmented matrix, which includes the constant numbers from the equations. These constants are separated from the coefficients by a single vertical line drawn in the matrix. Let's look at a couple of examples. Suppose we have the equations 2x plus 3y plus 4z equals 50, x minus 2y plus 7z equals 99, and 5x plus 6y minus z equals 22. What would be the augmented matrix for this system of equations? We take the coefficients and the constant from the first equation and place them in the top row of the matrix. We have 2, 3, 4, and after the vertical line, 50. We do the same for the second equation. The hidden coefficient of the x term is 1. Also, minus 2y means that the coefficient for the y term is negative 2. So the second row of the matrix will be 1, negative 2, 7, and 99 goes after the vertical line. And we need to set up the last equation. Again, we have a hidden 1, this time for the z variable. Entering our coefficients, we have 5, 6, and negative 1. The constant 22 we place after the vertical line. Let's look at one more example. What if we had the system of equations x plus y plus z equals 11, y plus 2z equals 3, and 3x minus z equals 2? What would its augmented matrix look like? For the top equation, all the coefficients are 1. So we have 1, 1, and 1 with the 11 after the vertical line. The second equation has no x term. We need a 0 in the x column, which is the first column. This row will be 0, 1, 2, and 3 after the line. In the last equation, we have no y, so we need to fill in the second column, the y column, with 0. We have 3, 0, negative 1, and 2 after the vertical line. There is other basic information we should consider before looking at the actual algebra of matrices. One such topic is the dimensions of a matrix. The dimensions tell how big is the matrix. It is written M, X, N. This is read as M by N. If a matrix has dimensions M by N, that means it has M number of rows and N number of columns. Let's see some examples. Suppose we have some matrices. Matrix A is 9 and 7, then 5 and 11. Matrix B is 7, 9, and 11, then 13, 5, and -2, then 6, 1, and 22, then 8, 65, and 47. Matrix C is 5, 11, 13, -4, and 6, then 8, 1, -3, 0, and 7. We want to find the dimensions of each matrix. Matrix A has 1, 2 rows and 1, 2 columns, so it is 2 by 2. Matrix B has 1, 2, 3, 4 rows and 1, 2, 3 columns, so it is 4 by 3. Matrix C has 1, 2 rows, but 1, 2, 3, 4, 5 columns, so it is 2 by 5. But what about the numbers inside the matrix? How can we identify each position inside the matrix? We do so with the notation capital A sub M, comma N. This means we want the number that is in row M and column N of matrix A. Let's look at an example. From before, we have where matrix B is 7, 9, and 11, then 13, 5, and -2, then 6, 1, and 22, then 8, 65, and 47. We want to find B sub 1, 2, B sub 2, 1, B sub 3, 3, B sub 4, 3, and B sub 3, 4. B sub 1, 2 means we want to be in the first or top row and the second column from the left. So B sub 1, 2 is 9. B sub 2, 1 is the number in the second row, first column. This is 13. B sub 3, 3 is in the third row, third column of matrix B. We have 22 in this position. B sub 4, 3 is the element in the fourth row and third column. For our matrix B, this is 47. B sub 3, 4 is the number in the third row and fourth column of matrix B. But matrix B only has 3 columns. This number does not exist.